The half-life of carbon-14 is approximately 5,730 years, and that means after that many years, half of the material has converted from the original carbon-14. So this is sounding like a decay problem. And so if an artifact that originally contained 100 grams of carbon-14 now contains 10 grams of carbon-14, we want to know the age of the artifact. And we're going to round our answer to the nearest 100 years. All right, so I just told you this was exponential decay. And this is all about radiocarbon dating. And I chose this problem because I think it emphasizes the usefulness of this type of thing, because we can find the age of very old artifacts, I don't know, like fossils or whatever. So we do need to focus on this term half-life, because even though they gave us this initial amount, which is 100 grams, they didn't give us the constant K, and we need that to solve the problem. So we have to use this information about half-life. And the way to do that is to kind of isolate T and plug in the 5,730 years for T to solve for K. In order to do that, we have to get rid of our Y's, and we're going to do it this way. So half-life basically means that half-life is the amount of time that it takes for half of the material to decay. So we have this initial amount y0, and then so that's going to equal half of y0. And we want to solve for the amount of time it would take to do that. So we can divide both sides by y0 to cancel them out, and we would get 1/2 equals e to the negative kt. Take the natural log of both sides. Again, that's going to cancel out our e right here. So then I'm just going to keep it white. And then so we're going to have natural log of 1/2 equals negative kt when we bring down that exponent. T is going to equal negative natural log of 1/2 divided by k. I just divided both sides by negative k. And that actually equals the natural log of 2 over k. The reason is because 1/2 is equal to 2 to the power of -1. And we know, according to the power rule, if we have that exponent, we can multiply it out in the front. So we're left with that 2 in the parentheses, and then the -1s cancel each other out, and we're left with natural log of 2. Okay, why does it keep going to the top? I don't understand that. All right, so they told us that the half-life is 5,730. So we're going to plug that in and finally solve for k. You would kind of switch these. So you would do the natural log of 2 divided by that 5,000 number. Now we could sort of approximate this, but it's better if we can leave it exact. So we'll just leave that for k. And now we have everything we need to solve the actual problem. So let me go back up to that. So we want to know if an artifact that originally contained 100 grams and it now contains 10 grams, how old is it? So we have everything we need for our function, which I can rewrite over here. So we have y equals, our initial is 100 times e, we have our k, and remember our k is negative. So negative natural log of 2 divided by 5,730, and that is times t. So that's our function, and our y value is 10. We have 10 grams left over. So we're going to plug that in and solve for time. Feel free to kind of try this on your own and skip ahead if you don't want to watch me do it. Okay, and we would divide both sides by 100. We would get 1/10 on the left here equals e to the power, I'm going to abbreviate that, times t. That's not really an abbreviation, I just did a squiggle, but it's easier. And so we would take the natural log of both sides. So natural log of e, I will write it this time. That crazy k number, and then times t. All right, so this would cancel out, and you would bring this exponent down. And then so you would divide both sides by that k value to isolate t. That's a lot of writing. So anyways, you would do that like division on both sides and then plug everything into your calculator. And you would get approximately 19,035 years. Long time. And we're rounding to the nearest 100 years. So our final answer would be 19,000 years. Yep, and that does it for, that's a lot of writing, and that does it for exponential functions. Thanks for watching.